So, have you ever designed a perfectly routed printed circuit board, carefully laid out every single physical trace, only to power it up and find it suffering from massive, inexplicable interference? Man, it's a mystery that haunts both junior and veteran engineers alike. Welcome to this explainer. Today, we're mastering magnetic coupling and interference, using the foundational concepts from Henry Ott's absolutely authoritative text, Electromagnetic Compatibility Engineering. You've got to ask yourself, why do circuits that look totally flawless on your computer screen still fail in the real world? Well, it's because the physical traces are really only half the story. To solve this mystery, we have to look past the visible surface and understand the invisible forces at play. We're going to dive straight into the electromagnetic environment that bridges the gap right between our circuits. Here's our roadmap for today. We'll cover 1. The invisible noise problem, 2. Inside inductive coupling, 3. The math of magnetic coupling, 4. Calculating noise step by step, 5. The magnetic v electric gotcha, and finally, 6. Key takeaways and our outro. All right, let's jump right into part 1, the invisible noise problem.
Moving right along to section 2, inside inductive coupling.
To understand how this happens, we need to look past the surface and zoom straight into the physical interaction. When a circuit fails due to inductive noise, it's literally because invisible magnetic fields are bridging the physical gap between your circuits. They're transferring energy where it absolutely does not belong. Think about it. When a current, let's call it I1, flows through a physical conductor, it creates a magnetic flux. This flux sweeps right across space and induces a noise voltage, Vn, in a nearby conductor. We can actually model this invisible physical interaction as an equivalent circuit using mutual inductance, which we denote with an M. So your interfering circuit acts as the primary winding of a transformer, and the receptor, well, that acts as the secondary. To really lock this concept into your brain, we're going to use a never forget visual analogy. I want you to imagine inductive coupling as an invisible magnetic wind catching the sail of a receptor circuit. The physical loop area of your receptor circuit, that's the sail. The magnetic flux density is the strength of that wind, and the angle of your circuit dictates exactly how that sail is positioned against the wind. It's a game changer when you picture it like that.
Okay, let's get into section 3, the math of magnetic coupling.
We are not skipping any steps here. Let's derive the rules. First up, the total magnetic flux, phi t, is simply equal to the inductance, L, multiplied by the current, I. Simple enough, right? Second, when the current I1 in our first circuit produces a flux in circuit 2, we define the mutual inductance, M12, as the flux in circuit 2, phi 12, divided by the current I1. Third, Faraday's law kicks in. It tells us the induced noise voltage, Vn, in a stationary closed loop with a sinusoidally varying flux is J times omega times B times A times the cosine of theta. Finally, because that B times A times cosine theta chunk represents the total magnetic flux coupled to the receptor, we can cleanly combine these expressions. So the ultimate noise voltage Vn simply equals J times omega times M times I1. Now let's break this down and map every single variable to its physical meaning so the math becomes incredibly concrete. J is our imaginary unit, representing a 90-degree phase shift. Omega is the angular frequency of the noise. B is the root mean square value of the magnetic flux density. Remember, this is our wind strength. A is the physical loop area of your circuit, the literal size of your sail. Theta is the angle of incidence, how your sail is angled to the wind. And M is the mutual inductance, which is this fantastic single term that accounts for both the geometry and the magnetic properties between the two circuits. When that magnetic field B cuts through the shaded area A at an angle, the solution to your noise problem becomes instantly obvious from our formula. To fix the interference, you basically have 3 physical options. You can physically separate the circuits to reduce B, you can route your return path much closer to your signal to shrink your sail area A, or you can reorient the components to adjust your sail angle theta. It really is that straightforward. Next up, section 4, calculating noise step by step. The text gives us the formula, but to truly see the mechanics of how it simplifies, we're going to explicitly plug in some arbitrary dummy values. Let's assume we're using the standard MKS system of units, just like the text strictly advises, where B is in Teslas and area is in square meters. Side note, if you ever use the CGS system, Gauss and square centimeters, the text warns you absolutely must multiply your result by 10 to the power of -8. Anyway, for our MKS mechanical example, let's just say B is 1 microtesla, the area A is 0.01 square meters, and our sail angle theta is perfectly flat at 0 degrees, meaning the cosine of 0 is just 1. The physical parameters of our formula simply multiply together right here into a constant baseline of vulnerability for a circuit. But hold on, here is the absolutely critical multiplier. That omega term in our equation, that equals 2 times pi times frequency. So what does this tell us? It means magnetic coupling is directly proportional to frequency. If your interfering current doubles in frequency, your induced noise voltage Vn exactly doubles. Literally, higher frequency signals create proportionally worse magnetic interference. You have to watch out for that.
All right, let's talk about section 5, the magnetic vs electric. Gotcha.
Listen, you absolutely must diagnose which invisible force is attacking your circuit before you can even hope to fix it. This trips people up all the time. Here is the golden rule. Electric field coupling acts as a parallel current source connected between your receptor circuit and ground, but magnetic field coupling, which is what we've been deep diving into today, creates a noise voltage directly in series with the receptor conductor. Do not mix those up. Let's actually use the equivalent circuits to visually prove this difference. Electric coupling injects a parallel noise current, IN, while magnetic coupling induces a series noise voltage, VN. Because of this massive structural difference, Henry Ott gives us a brilliant diagnostic test. Here's what you do. You measure the noise voltage across the impedance at one end of your cable while actively decreasing the impedance at the opposite end. If the noise voltage decreases, you're dealing with an electric field because you're literally shorting out a parallel current source. But if the noise voltage increases, boom, your pickup is magnetic. Why? Because you are drawing more current from a series voltage source. It's such a clever test.
And finally, section 6, key takeaways and outro.
Man, that diagnostic test alone will save you hours of debugging in the lab. All right, let's do a rapid-fire recap of everything we just learned. First, magnetic noise is strictly governed by the equations Vn equals j omega mi1 and Vn equals j omega ba cosine theta. Second, never forget the sail analogy. To minimize noise, physically reduce your loop area A or adjust your angle theta. And third, the gotcha. Magnetic coupling always creates a series voltage source, while electric coupling acts as a parallel current source. You now have the mathematical foundation and the physical intuition to master the invisible forces disrupting your circuits. Hit subscribe for more EMC and automotive communication protocol survival guides. But before you open your CAD software today, I want you to ask yourself one question. What invisible magnetic winds are currently blowing across the most critical traces on your PCB? See you next time.